Yeah, thank you very much. I'm very grateful to Carlile and to Nathan and to Antonio for inviting me to give this tutorial. This is not exactly new in the sense that the first time I put these slides together, it was in Sen-Maki in 2017. So this is an evolution of those slides. And that time, I mistimed my intervention, and I guess I only presented a part of the material. This time, I probably have more experience presenting this material. Hopefully, I'll get to the end, because the end is the real link with data science today. In the end, I will give this away. I will apply certain methods that I will have presented during the talk to the input of a neural network. And I will show that it works better if you use distance geometry instead of what people use currently. All right, so my argument is that usually data are well represented by graphs. By data, I mean the kind of data you find, for example, in a database. So where you have columns, you have entities, you have incidences between records and features. You have all sorts of combinatorial things that are well represented by a graph. But also data such as images are well represented by a graph. There's many methods to do stuff with graphs. When you have data on graphs, for example, you could cluster them with modularity clustering. You could analyze them in all sorts of ways. However, there's a lot of methodologies for machine learning today that are under the scrutiny of the whole community, such as neural networks, but also support vector machines. Also other things, even just logistic regression, which is the simplest sort of supervised machine learning. These methods require vectors in input. Okay? So how do we turn a graph into a vector? And this is exactly where distance geometry comes into play, because this is exactly the science of drawing graphs into some dimensional vector space. Okay? So instead of doing what people do today in order to turn graphs into vectors, and I'll show you what it is, I decided to try, because this is really experimental. Okay? I don't have any indication that these things are better or worse. In fact, some of them are worse. Some of them are better than what is being done today. I tried to turn them into vectors the way I knew how to, and this is an account of what I obtained. So first of all, the problem itself, Euclidean distance geometry. The Euclidean distance geometry problem, or the distance geometry problem, the light is in the middle? The trigger, okay. All right, so the distance geometry problem is basically how to draw a graph into a k-dimensional vector space, where k is given, so that all of the edges of the graph are drawn like segments, and the weights on the edges are the same as the length of the segments that represent each edge. Okay? So this is what it is. It's something to do with Euclidean distance. You can also draw graphs according to other distances, and we'll see, actually. But this is the setting here with the Euclidean distance. Notice that k is part of the input. In the Euclidean distance matrix completion problem, k is part of the output, and the complexity class changes. Now, about complexity, well, first of all, some applications. I'm not going to go through these applications now because I decided to use them as intervals. So I will give you respite from all my talking by talking some more, but about the application instead of the theory. And this probably should sort of relax you a bit. You can distract yourself for a while. You can rest or whatever. OK, so complexity classes. So there are these two complexity classes that are very famous, P and NP. OK? So P is the complexity class of all those algorithms, or sorry, of all those problems for which there exists an algorithm that runs in polynomial time. And we're talking about decision problems here. And NP is the class of the problems for which there is an algorithm that runs in polynomial time on a non-deterministic Turing machine. So non-deterministic Turing machines are things that don't really exist. They are just abstract. And basically, it's as if a computer were able to follow the path of each branch, of each if, then, else, in parallel. Okay? So this is a non-deterministic Turing machine. So of course, they're perfect for doing complete enumerations of sort of a combinatorial 0-1 problem in polynomial time. Okay? Because essentially, you can test all of the configurations in parallel pretty much, and that will be it. An equivalent definition is that there should be for yes instances only of these decision problems, there should be a certificate, okay? And this certificate is something that says that you can check to verify that the instance is really a yes, okay? If it were like the max click, the click problem, then I would give you, I would exhibit you the click. And then you can check that it is a click because you have the graph, the initial graph, the edges, and you can check. So these two classes are important in computer science because they tell you more or less what is doable and what is not doable asymptotically. Now, DGP, the distance geometry problem with this index k, is the distance geometry problem where k is being kept fixed. Okay, so k is usually fixed in application. It's usually 2 or 3, the plane or the space. There's other situations, but those are the most common. So the DGPK may not be in NP for k greater than 1. This is because we don't really know how to represent the certificates, okay? So the certificates here may be in the plane or in space or in higher dimensions. They may be irrational numbers and algebraic numbers, in fact, because this problem is about solving a system like this one, okay, with squares here. So this is a quadratic system of equations. And the solutions you might get are algebraic numbers. There are some finite representations of algebraic numbers, such as, for example, their minimal polynomial and then the closest rational point to the root. However, you know, I checked some of these easy representations, and I could always construct infinite classes of graphs such that this representation gave, in order to check this certificate, it took me more than polynomial time. Okay, so these representations are not the right representation. While I don't know whether there exists a representation that works for all graphs or not, I cannot say that it is an NP while I don't know it. So we don't know. All right, so DGP1, on the other hand, this is DGP on the line. Okay, you can only do left or right as decision. There's always reflections. There are no rotations. So in this case, we do know that it's in NP. Because essentially, suppose suppose one of the points were at an irrational value, okay? You could still translate it to a rational one, and magically, all of the other points would translate also to rational because the distance values are rational, meaning that the input here has to be rational in order to qualify as a decision problem for which where is it here? Okay, I write R here, but in fact, the Turing machine model would require me to write Q, okay? On the other hand, most of the stuff that we say about the complexity of this problem or problems related to this is intended to be in the real RAM model. This is basically another abstract machine that doesn't really exist where you can do unit time transformations on real numbers, okay? So we sort of discount these complexities, these numerical complexities. Our certificates are sets of real numbers or matrices full of real numbers, and we say we can check them when we can check them at the, I don't know, third decimal digit or something, and we're hoping for the best. All right. So in fact, this DGP1, not only it is in NP, but it is also NP hard. What does it mean to be NP hard? And I'm saying this because maybe there are some students here who may not know, so I'm getting into this is tutorial, okay? NP hard, it means that every problem in this class NP has a reduction to your problem, okay? So there cannot be any sort of provably harder problem because you could solve any problem in the class by just solving yours. First you have another problem, you reduce it to yours, you solve yours, okay? If yours was easier than some other, you would have reduced a harder problem to an easier problem, which is impossible. So essentially, NP hard means it's as hard as all of the problems in the class, including the hardest problem in the class, which we may not know what it is, but it's certainly no easier than this problem, okay? So the reduction here is from partition. Partition, you give yourself a set of n integers, and you want to decide a set of indices I, such that if you sum over I all these integers, you will get exactly the same value of the sum as if you sum outside of I, okay? So this is known to be NP hard, NP complete. When I say NP complete means that it's not only NP hard, but it's also in NP. So we're talking about the DGP1, and this we know it's in NP. And now we're proving that it's NP-hard. It's only a sketch of the proof, but essentially you reduce this problem to a subset of DGP instances, which is just the DGP instances on cycle graphs, okay? And the cycle graphs, essentially, you can follow a path and go back, okay, on the combinatorial part of the problem, i.e. the graph. Now, imagine that you have laid the graph on a line, okay? And then you have to position the points, and you can only decide left or right, okay? So you decide left, and then you decide the second edge. For example, from 1 to 2, you decide to go on the line, you decide to go right, and then from 2 to 3, you decide to go right again, and then 3 to 4, you want to go left. And the game is that you have to go back to 1 at the same point that you used to start with, okay? So these choices left and right, you can see that it's a combinatorial thing, and you can see that potentially there should be a need to test them all. Meaning that it's not exactly evident that you might go back to easily to the first point that you started from. Okay, so this is the reduction, and this left and right choice is precisely what reduces yes, yes, no, no to this, because this is the choice of taking an index in I or leaving it outside of I. Okay, so this is the kind of reduction. I'm not giving any more details, but it's not too hard to see. All right, so after this brief stint of theory, let me relax you with the application of DGP in one dimension, which is basically something to do with time, okay? So we are on the timeline, and you have to decide, you have a set of watches, a set of clocks. Imagine there are some sensors. These sensors are being parachuted in some place very, very difficult. It's hard to keep connectivity, but you have some sort of connectivity between these mobile sensors, wireless sensors, and you can't use too much battery because you've parachuted them in some crazy desertic region where there is nothing, and they have to survive for years or something like this, okay? And so in trying to minimize the kind of the amount of communication between these sensors, you want to design protocols that really exchange the minimum amount of data for basic tasks, such as synchronization, okay? So each sensor has a clock, and they need to be synchronized. So there is one sensor that is linked, for example, with a wire, or that has more battery and communicates with the external, with the controller. And then this clock communicates maybe just the time, knows what the time difference is with the clocks, the other clocks that it can communicate with. For example, here we have this clock that can communicate to that one, okay? And it knows that there is a time difference between Alice and the atomic clock of 5, okay? So this is what is being exchanged on the protocol, a simple scalar, the time difference, not the whole timestamp. And then, you know, this graph of connectivity is essentially something that needs to be embedded on the timeline, okay? Because this knows its absolute times, but the others don't, and they have to reconstruct it. And so here, the possibility is to place Alice either right or left of the atomic clock. And the same goes for the other clocks, okay? So this is a real application in the sense that there are real papers talking about it. I don't know if there are also real networks that use it. I don't know. All right, so now let's talk about how to solve this problem, the distance geometry problem. And the first thing, the first material that I want to present to you is basically methodologies that come from mathematical programming. Now, I think most of you know what mathematical programming is. I don't know if the students do. Do you know what mathematical programming is? Anybody not know? Okay, so mathematical programming is essentially a formal language for describing optimization problems, okay? So, like a formal language, there is a grammar, there are valid sentences, there's a whole syntax, you can put together expressions, you can say this is an objective function, there is the cost to minimize or some gain to maximize, there is an optimization direction, there are constraints, and these constraints can be either implicit, like when I say this variable is integer, or explicit, like when I say this function of these variables has to be less than 0, something like this. And there are decision variables, and the decision variables basically encode the output of the problem. And then there are some parameters. The parameters encode the input of the problem, okay? So you can write this sentence, and then you can replace the parameter symbols with values, okay? And then you have something that you can pass to something, you can pass to a software. This software is equivalent to the interpreter or the compiler, but it's called a solver, okay? So you pass this sentence of a formal language to the solver, and the solver places, looks at the input, looks at the formulation, and places, after much toiling, the values of the output into the decision variables, okay? So this is mathematical programming. It's not only a language, it's a language you can use, but it's not an imperative language, it's not a declarative language, it's a descriptive language, okay? So this is like a description of the optimization problem that you want to solve. But this description is functional. You can pass it to a solver and get an output, okay? All right, so the first formulation is the very simplest formulation of this problem. It's basically you want to solve a set of equations that say this is equal to that, okay? And instead of solving that set of equations, you penalize their square differences. Notice that when somebody mentions penalization of square differences, people usually think convex. This is not the case. Here, the variables are inside a square term itself. So after you square this, it becomes quartic, okay? This quartic form is not convex. In fact, it is non-convex, and it's got many local minima and also many global minima, all right? However, it has this property that because it's a sum of squares, the whole polynomial is non-negative, okay? So essentially, when it reaches 0, it means that, well, it reaches 0 if and only if all of these constraints were satisfied by the values of the variables, okay? So this certifies its own global optimum in this way. Is this a good formulation for solving? Like, you know, are solvers capable of solving this well? In general, I don't think it's very bad. I think it's actually quite good. Although it's got many minima, it doesn't have any constraint. Okay, so essentially, it's like an unconstrained formulation, which is one of the simplest. It requires a software that may not be all that sophisticated to solve it. Okay, so and then there are some solvers that are very sophisticated and solve it well also. Usually, the solvers that can solve this thing fast do not locate the global optimum. They locate a local optimum. However, if you choose your starting point for the software correctly, or if you're lucky enough to choose it well, then maybe you're not too far from the global optimum, and maybe one local descent or maybe a few local descents may help you get there, okay? So it's not a bad formulation for improving on something you already have. All right, so one thing that we can do to that formulation is to reformulate it. So I told you this is an expression in mathematical programming, so it's a sentence, and this sentence is interpreted by the solver, and it gives you the solution. But there's something else you can do. Because this is a formal sentence, you can also take the symbols and apply some logical identities to some of the expressions, okay? And then you can transform it in ways that are certifiably the same thing, but written differently. And the interest of doing this is that solvers will actually perform better or worse depending on the formulation, not on the semantics of this sentence, meaning not on the feasible set that is not changing, or not of the optima that are not changing, but really on the expression that you write. And these are called reformulations. All right, so we can reformulate these things. For example, one thing that we can do, instead of penalizing the square differences, we can penalize the norm 1, okay? So the absolute values of the differences. And this is what I did here. Now, the absolute values, you can sort of decorporate or scorporate the negative side and the positive side, okay? And so then you can say, all right, so the positive side, I don't want it to be greater than its limit. And the negative side becomes a maximum of the positive side, because min of f is equal to minus max of minus f, all right? And then you come up with this formulation. So this formulation is still complicated, because this is a maximization of a quadratic form. Now, a quadratic form that is also convex, okay? But a maximization of a convex form is a concave problem, and it's still NP hard to solve. It's not a simple problem to solve. However, it's got this benefit that this is no longer quartic, it's just quadratic. We know a lot more about quadratics than we do quartics. And the constraints are convex. They define a convex region, okay? It's an intersection of these balls, essentially. So this form can be exploited in other ways. And I'm not going to go into details because I don't have time. All right, so what else can we do? We can relax this problem, okay? I've talked about these problems being non-convex, concave, reverse convex, etc. These are hard problems. So one way to ignore this complexity or this complication is to use a solver that only runs locally and stops. And another way is to relax some of the terms, remove the non-convexities, and solve what's left. Like, for example, what we do here. Okay, this is the initial system, and now I am rewriting this part like that, and you can recognize it to be the same. And then I do something that is called linearization. In linearization, we reformulate every nonlinear term that we don't like, or any term that we don't like, by a single variable that is added to the formulation. Okay, in this case, these are the big X variables. Okay, so for each product, xi times xj, and these are the same things where I is equal to j. Okay, but for each of these products, I introduce a new variable, big X, index with two indices, I and j. Right? And I linearize this equation. This equation is nonlinear. Suddenly, this is linear in the big X's. And then I also have to say that xij is equal to xi times xj. And this is what says it. So I haven't changed the complication of it, meaning that this term is very non-convex, but this is at least linear. Okay? So instead of writing this, I can also write the fact that x minus xx transpose is the zero matrix. It's equivalent, okay? And instead of writing this, I can relax it by saying that x minus xx transpose has all of its eigenvalues non-negative. This is a heck of a reformulation. It's not, it relaxes a lot, okay? So instead of requiring all of the eigenvalues of this matrix to be zero, I'm requiring them just to be non-negative. So there's a lot that is lost. But in fact, it turns out that in practice, this is a very strong reformulation for quadratic problems, okay? So instead of writing this, I can also write this, and then I can pass this problem, i.e. these linear equations subject to this constraint to a solver, which is called the semi-definite programming solver, okay? And this solver will find the global optimum of the reformulation, which is now a convex problem, okay? In reasonably polynomial time. What do I mean by this? It's not really polynomial time in the Turing machine model, okay? But it's polynomial time to get to any given epsilon that you might imagine. This is not for free. It comes with conditions. Abdo was talking about the Slater conditions. So there are conditions. But in practice, lots of people just ignore it and hope for the best. Okay. All right, so this is the relaxation that I propose. Notice that semi-definite programming solvers, they also allow you to specify an objective function, same thing as Abdo mentioned. And this objective function really depends on the application, okay? So in the case of proteins, for example, after a few tests, I realized that this is a pretty good objective function to use. But then I guess it also depends on the instances. So this is just an empirical choice. All right. So what happens when SDP solvers hit their size limits, and do they hit their size limits? In fact, yes. Unfortunately, so SDP, semi-definite programming, is a good formulation because it can be solved in polynomial time at least to a desired accuracy. However, this is not exactly enough, meaning that for many, so we have added a new variable for each pair of old variables. Okay? So in fact, when we started from n variables, now we have n squared variables. It's a lot more variables. And SDP solvers, unfortunately, have a size limit, meaning they increase their complexity like n3, n cubed. There are many algorithms that grow like n cubed, but we use them successfully with thousands of entities. Well, SDP doesn't seem to be one of those cases. There are some other algorithms that can sort of reduce the size and get you to a more acceptable size. And facial reduction, if I'm not wrong, is very successful in that. But let's stay on the simple empirical things that anybody can do meaning that you can sort of get an off-the-shelf solver. I don't even know, do you have an off-the-shelf solver for facial reduction?
Depends how polished
Yeah.
shelf means.
Yeah, okay. Right, so there are some codes around. I think there's a MATLAB code that one of your students put out. No, Nathan. Where is Nathan? Yes, you put it out, right? And I once told you that I didn't see any code to an SDP solver, and you told me there's never any need. Yeah. So this is an incredibly successful algorithm, meaning that this is supposed to cut down the size until you can't anymore, and then you call the SDP solver. Okay. However, they never found an instance where calling the last solver of the SDP solver was needed. So very successful. But you have to know what you're doing. You have to at least understand how Nathan writes his code, et cetera, et cetera. So if you want the off-the-shelf solver that you can simply deploy, I imagine that you have to use the interior point method. Okay, so anyway, so this solver is not as good at tackling large sizes. So there's this paradigm that I call diagonally dominant programming that was proposed by my friend, who should be here today, but is not here yet, Amir Ali Ahmadi. And he has no excuse because he lives and works in Princeton, which is just down the road. So a diagonally dominant matrix is something that is a matrix that obeys this. Okay? So basically, the diagonal is larger than the sum of the absolute values over the rows, okay, excluding the diagonal element. And it's got an interesting property insofar as diagonally dominant matrices are automatically positive semi-definite. Okay? So if you're optimizing over the cone of positive semi-definite matrices, which is what we do when we employ an SDP solver, you can also approximate that cone from the inside, yeah, by saying I restrict myself to those matrices which are not only PSD, but in fact they have something more, they are diagonally dominant. Why would I want to do that? Because this characterization is much easier to deal with than the characterization of a semi-definite, of positive semi-definite matrix. Why is it easier? Because this thing is linearizable, okay? So there is a term I don't like. The only nonlinear term, this is the absolute values, okay? So I do what I did before. I linearize it. So I replace absolute values of the components of x by a new variable t, which is a matrix variable, same size. And then I add these sort of sandwiching constraints, minus t less than or equal to x, less than or equal to t. Okay? And then you can show that the polytopes of this reformulation is the same as the polytope defined by the original constraints. So instead of writing this, we can now write this, and this is completely linear, and this is also completely linear. So this is what we obtain. This is a diagonally dominant programming formulation for the distance geometry problem. Okay? And why is this interesting? It's interesting because this is an LP, a linear program. And linear programs can be really solved efficiently by these extremely successful off-the-shelf solvers such as Cplex or Gurobi or ExpressMP. Okay, so yes?
Sorry to interrupt. So this is not a convex relaxation.
No.
It's more like a convex restriction.
Exactly.
Like,
yeah. It's a linear restriction of a convex relaxation of a non-convex problem. So what relationship is there between this problem and the original problem? None.
Usually you have successive outer.
Usually you do.
Like,
I'll get to it. I'll get to it. So this, if you're lucky and it gives you a solution, it is also SDP. It is also PSD. The matrix will be PSD automatically. So it's interesting empirically, okay, because of that. However, the original SDP might be feasible, and this may be infeasible. So in that case, it won't help you, okay? However, there is something else that you can do. Every cone has a dual cone, okay? So if you take the dual of this, you can show that this new dual formulation is a convex relaxation, a linear relaxation of the convex SDP, okay? So in that sense, I can also adapt this. But however, I lose the diagonal dominance, okay? The solution of the dual will not yield something that is PSD. It will yield something, a matrix, that may have a large negative rank, unfortunately. So it's a choice. It's something you can do cheaply. It's a cheap trick. you relax, and then you approximate, and then you do this, and it's fast to solve, and then if you're lucky, you get a solution. This is the game. All right, so end of another part, and let's see the application in 2 dimensions. Sensor network localizations. Why is it in 2 dimensions where Abdo presented it in 3? Because he was thinking of parachuting sensors with balloons that stay in the air. Or maybe he was thinking about parachuting sensor on a ground that is mountainous. But even a mountainous ground is a 2-dimensional manifold. So I could also argue that it's in 2D. The reason why I actually argue that it's in 2D is because it's used sometimes to locate things in an office, for example. Okay? So you are a boss and you're evil, like Cuthbert, the human resources manager of Dilbert, and you want to know at each point in time where all of your employees are in order to play cheap tricks on them. And then you give them a free telephone that doesn't call, but just communicates with all the other telephones and knows how distant they are because they use so much battery, okay? So if I'm here, my telephone communicates with Nathan's, and then it uses very little battery, and then it also communicates with Carlile, and it uses a little more. So we know an estimation of these distances, but it cannot communicate with, for example, with Abdo. He's too far, okay? So then there is this connectivity, and you want to retrieve the position of all the sensors, okay? So this is a distance geometry problem where you have a graph, and it is connected, and you need the positions on this floor. Okay, so remember what I said so far is that you can solve the original problem, but it's non-convex, and then you can have these reformulations and these relaxations, which, however, give you as an output matrices rather than vectors, okay? Now, when I say vectors, it's not completely correct, because in fact, when I want to solve the distance geometry problem, the output is a set of vectors, okay? I want to embed each of the vertices of the graph into Rk, okay? So I have n vertices to be embedded in Rk. So this is a matrix, it's not a vector. A matrix that is n times k, okay? We have n times k, it's like a slim matrix, and each row is a vector, and the ith row is the position in Rk of the ith vertex, okay? So this is a matrix, but it's n times k, so it's got rank at most k. Whereas the SDP that I presented before, and also the DDP, the diagonally dominant program that I presented before, they give me matrices that are n times n, okay? If I interpret them as being, for example, realizations, okay, it means that I would be embedding in Rn, which grows with n, whereas k is being kept fixed as I don't know, 2 or 3. So it's not exactly ideal. So how do I retrieve an R times k matrix from an n by n matrix? I do it heuristically and approximately. So there are 2 methods that everyone who takes a course in either statistics or data science must already know, but this is a tutorial, so I'll still go through them. And they're called classic multidimensional scaling and principal component analysis. I see them as almost the same thing, okay? And thanks to Abdo, and also I think thanks to someone else, maybe David, I don't really need to say much. So there are these 2 things that you already saw 3 times, okay, these 2 relationships. And the point is that you can transform a squared Euclidean distance matrix into a gram matrix linearly, okay? So there's a one-to-one correspondence. So what does it mean in practice? It means that when you get these, where is it? Yeah, so you get something like this, okay? And this is your distance matrix, and you're discounting these norms, and you're really just looking at these things, okay? In fact, you're not even discounting the norms because they're just the same xi times xi and xj times xj. But in fact, the information is all in the gram matrix. The gram matrix, by the way, is a product of the realization n times k times its transpose, okay? So this is the ith, jth component of this gram matrix is exactly, they raise the temperature.
Yes.
And I start with the stripping. So there is no measure in this thing. Huh? First they go at -10 and then, oh, okay, they asked 3 times. Now I'm going to switch them off completely. Okay. So the gram matrix is essentially, has the same information as the distance matrix, okay? Arranged differently. Okay, so what can you do with the gram matrix? Well, the gram matrix is a product of the realization times the realization transpose. Okay, so you can factor it. You can factor it using spectral decomposition, which is what has been done already this morning a couple of times. And what you obtain is something like this. You have this G tilde, which is sort of an approximate. Why do I say an approximate gram matrix? Because these methods actually are used when you don't have a distance matrix, but you have something that you've estimated because you thought it was right. Okay, so you may have, for example, a set of preferences. You may have something that has nothing to do with numbers, and they ask you to paint it in a plane. Okay, to draw it in a plane. So you do your best to sort of quantitatively evaluate distances, differences, similarities. So maybe these numbers you've produced in your own head, you don't even know why, okay? So this is a very approximate distance matrix. This is actually used a lot in industry, where in order to give depictions of situations that the boss might understand. The same boss, maybe not Cuthbert, because Cuthbert is smart, but the pointy-haired boss, for example, who's completely idiotic, would not understand a set of preferences, but he would understand a set of points in the plane on a piece of paper. So these things are actually done, and there's a real need in industry for giving planar depictions of situations that are extremely complex, okay? So you have this D tilde, which is actually an approximation. It's not a real distance matrix. And then you do this thing. You can always do it. There is nothing against stopping you from doing this thing, this transformation. And you get something which is not obviously a gram matrix. It's an approximation of a gram matrix. And you're hoping for the best, okay? Hoping for the best means that when you get the spectral decomposition of this gram matrix, you get a diagonal eigenvalue matrix, which is not positive semi-definite, okay? Some of the eigenvalues will be negative. This is otherwise it would be a perfect matrix there. So what you do instead is you approximate it to the closest PSD matrix. How you do this? All of the negative eigenvalues in this lambda are set to 0, okay? And this is the best you can do. This is how do you actually get the realization is this. From P lambda tilde, you zero the negative part of lambda tilde, and then you can, after you zero it, you can take the square root, because now the diagonally only contains non-negative things. Okay, and then you take P times the square root of lambda, and this is the approximate realization. Okay, so the rank is the number of positive eigenvalues of this diagonal. But if we wanted exactly rank K, this is still not good enough, because the rank is imposed here by the method. So instead, you zero even more. You just live with the K biggest eigenvalues. Okay, and there you go. So this is essentially multidimensional scaling with fixed rank. All right, so there's one other method that you can use in order to turn these STP matrices into the solutions of these STPs into matrices of a given rank. And this is an algorithm, a little known algorithm by Barvinok that we adapted to work in rank K. Barvinok wrote it for rank 1. It's based on the concentration of measure, which we also heard before. You mentioned it. And this concentration of measure is basically a phenomenon that relates to the law of large numbers, if you will. Okay? So when the variances decrease with size, when the discrepancy from the average of a quantity decreases with size, and it decreases in a certain way, then we can say that there is concentration of measure. And this way is the following. Suppose you have a function f that maps into the reals, okay? And this function has an average over all of its values, okay? And you want to know what is the probability that the discrepancy between the values of a function and its average exceeds a certain epsilon. This probability decreases to 0 really, really fast, exponentially fast, okay? So you have these terms, and the important terms here are in the exponent, the negative exponent, and essentially as epsilon becomes smaller, this thing gets smaller and smaller, okay? Usually there is also size here. But here in this introductory slide, I don't have any parameter related to size. But I do have it here. So this is Bar-Vinok's theorem. The setting is basically that you have to solve a set of quadratic equations, okay? So there are these manifolds, each of which is related to a single quadratic equation. And this is a decision problem. You want to know whether this, the intersection of all these manifolds is empty or not, okay? And in order to find a solution, you might want to formulate an SDP, so relax this thing. And so you relax it to a set of linear equations in these linearization variables, big X, like I did before, subject to the fact that X is positive semi-definite, okay? So you get a solution, and this solution is called X bar. So this is, Bar-Vinok's algorithm says this. All you have to do to reduce this thing to rank 1, okay, so he worked it out for rank 1, is you factor you factor X bar, and the factor is called T, okay? Factoring means spectral decomposition, okay? Spectral decomposition, you take a factor. And then you sample a vector Y, this is a vector, from a multivariate normal distribution that is standard, okay? And then you post-multiply your factor by this vector, okay? And then you obtain another vector, a vector that I called X prime. It's a very simple algorithm. There is nothing to choose, nothing to loop. It's just two expressions, two lets, two assignments. But he claims and he proves that there exists this universal constant C and some n0 after which the following holds. And the following says that the probability that for every one of these manifolds, the distance between X prime and the manifold itself is less than this quantity exceeds 90%. Now, 90% is not really a magic number. There are some parameters that you can adjust in the proof in order to make this number as big or as small as you wish. I think he chose 90% because it's like comforting to the human. I don't know, something like this. But what does this say? This says universal constant times square root of something like logarithm of n. And this is very comforting, right? Because this thing will never exceed like 6. For any possible n that you can imagine at a human or universal scale, this square root of logarithm of n will never exceed 6. So that's fine. This is bad. This is worse, because your solution here, you have no guarantees. It depends on this data Q. So this could actually get higher. And in fact, yes, I mean, if you apply this, you do realize that after a certain n, solutions could get slightly worse, okay? But the important thing is that this is a statement on the distance, okay? It's very likely that my distance from these manifolds will be short, will be small, okay? So if we are close to the manifolds, this is a typical situation where I would use a local NLP solver with a starting point with X prime, and then do one single round of local descent, and hope to get very, very close to the intersection of the manifold. And it does work. The only problem to apply, I mean, this can be applied almost verbatim to the DGP, okay? Because these things are generalizations of my DGP constraints. However, the whole theory is worked out for Y being one-dimensional. So these are embeddings in the line, if you will. There is no big K parameter here. So we had to adapt his proof, which was non-trivial. A trivial adaptation would have been possible. When you sample this Y, you sample it from a normal distribution that has n components and not n times k. So when you do t times y, you have n times n times 1, okay? And it gives you n times 1. We would like this to give n times k. So y should be n times k and not n times 1. So one simple solution could be to stack all of these k columns into an n times k vector, okay? But this would require then these q's to be enormous, n times k times n times k, okay? And this is not good for SDP solvers. So this is not a good way to go. We had to rework the proof, and it was slightly more complex, but essentially doable. The really hard part was that he sketched the proof. So his proof was like, I don't know, half a page where everything, or maybe a page and a half, but maybe less than that. But essentially, he said that everything was obvious. I mean, Alexander Barvinok is a great mathematician. I really love his work. But most of the things he finds obvious takes me, I don't know, 6 months to understand. So essentially, it's not really suitable for me. So we, with a student of mine who is really brilliant, we tried to understand it. We almost understood it and then had to resort to his help. He was very, very happy that we were using his results for these things, so he gave us his help. And then we also improved on his result a little bit, but this is outside the scope of this talk. So anyway, so the application to the DGP is that I have manifolds xij, each one of which is the satisfaction of a single constraint for each of the edges, and then the DGP can be written as this, so is this empty or not? This is the SDP relaxation, we've already seen it. And then essentially the only difference is that I sample from n to the nk, so this is a matrix now, n times k, with average 0, which is crucial, but also a scaling factor. This scaling factor is also very important, 1 over square root of k. And then Barvinok's theorem works in rank k. So the heuristic is that I do all this, and then I take x prime as a starting point for local descent. Okay. End of another section, and my favorite application, which is the realization of proteins, okay? So you've already seen David's talk, and he presented these diagonal banded matrices, and he said this is typical in protein structure. It's true. These proteins essentially have a backbone, okay? And the molecules on the backbone, the atoms of the backbone have an order, the backbone order. This order can be used to infer some of the distances between these atoms fairly precisely, and some of the distances not so precisely because they're inferred in a different way using nuclear magnetic resonance. Okay? And then you may have other distances because the proteins fold in space, and then maybe you're measuring something that is, after a few folds, the backbone could be very close to another part of itself. Okay, so here, nuclear magnetic resonance would measure some distance, okay, but this distance is very close in Euclidean terms, but it's very far on the manifold of the fold of the protein. Okay, so you may have extra distances here and there. Okay. All right, so what else can we do in order to solve this problem, the distance geometry problem? Distance completion. So we've seen in the previous talk how distance completion can be almost equivalent to this distance geometry problem. The Euclidean distance matrix completion problem usually doesn't require you to work in a certain rank, but in David's case, he said, I want my solutions to be in a certain rank. So in his case, it was completely equivalent. Okay, so instead of working with graphs, you work with an adjacency matrix, weighted adjacency matrix. But there's something else that you can do. Well, first of all, there is this isomap heuristic. So isomap is really a dimensional reduction algorithm. Okay, it's a heuristic. However, this dimensional reduction algorithm starts with a set of points and then builds a graph. In my case, in order to adapt it to the distance geometry problem, I simply have to ignore the first part. I don't start with a set of points, I start with a graph. And I want to find the realization. Now, look at this picture, okay? So this picture presents a set of points, and in fact also a graph that connects the points, but it presents a set of points that lives on a one-dimensional manifold, but this two-dimensional manifold, but this manifold is actually non-linear, okay? So if you wanted to measure distance between this point and this other point, okay, if you measured it in the Euclidean distance in R3, you would make a mistake with respect to what the points really mean, okay? In fact, the proper distance from this point to this other point, if you're staying on the manifold, is this distance here, okay? And the researchers who have proposed this, this heuristic, Tenenbaum and other people, they recognize that on certain graphs that are they're called disk graphs. They are constructed locally by patches. If you've studied some analytic topology, you know about charts and atlases. This is sort of like that, but in the discrete world, okay? So you have disks, and you have some overlap between the disks. And this local way of constructing graphs gives you something where if you look for the shortest path, you will get quite close to a Euclidean distance, okay? As you can see in this part here. Nelson, you're distracting me, please. I know, but you're distracting me nonetheless. Ask a question. Come on, like a school. We are a primary school. Nelson, tell everyone what you wanted to ask.
No, just ask about the distance between how complex is that is interesting.
Okay. Well done. All right. So in order to find all shortest paths, you can use another n-cube algorithm, which is called Floyd-Warshall. And unlike the interior point method that solves SDPs, the Floyd-Warshall algorithm is an n-cube that actually works pretty fast. And it's also the most deceivingly simple algorithm that you may implement, okay? It's basically 3 loops, one embedded in the other, and a single if. But if you get the order of the indices wrong, you will get completely lost, and you will never find it. Anyway, so we start by looking at all shortest paths, and in fact, we don't even need the paths, just the distances, okay? And then we have completed this distance matrix for this graph. Once we have completed the distance matrix, we can just simply apply multidimensional scaling or PCA and get a realization either in some low dimensional space, but we don't know what rank, or because we've decided the rank. And this also is a heuristic that works pretty well. And this is incredibly the simplest heuristic. The Fress embedding is the simplest heuristic that I could find, and it's the one that works best for machine learning purposes, okay? I don't know why. I have no idea. But this is very, very simple. So we start with a metric space, any metric space, okay? It doesn't even need, it's not, suppose these are like, you know, they're not points in space. They're really like objects in your pocket, and the distance is whatever number you guess. But these numbers collectively obey the metric axioms, okay? This is the only requirement. Any metric space, okay? And you want to embed this metric space in some, well, in RK, but let's say in some Euclidean space, okay, for the moment. But faithfully, so that the distance matrix of the original metric space must be the same as the distance matrix as you're embedding, okay? So what exactly do you have to work with? Imagine you have this metric space, you can compute all distances. So the only data you have are those distances. So the Fress embedding is really, really simple. It says, okay, so this n by n matrix, which is the distance matrix, is in fact the embedding itself, okay? So the first line, or the first row or column, because these are distance matrices, so they're symmetric, the first row is the embedding of the first vertex. The second row is the embedding of the second vertex, and so on and so forth until the nth vertex, okay? So really, you use the distance matrix as if it were a realization, which is pretty crazy. However, it turns out that if you embed it within L infinity, okay, so this is an embedding in n dimensions, so it's a very high dimensional embedding, okay? But if you embed it within the L infinity norm in L dimension, this is an isometric embedding. All of the distances can be respected. It doesn't matter what metric space you start from. You can still embed it precisely. The proof is also simple. I don't have it here because this is a tutorial and I didn't want to give you too much, you know, too many details. So this is a long tutorial, so I wanted you to be sort of fresher instead of more stressed about it. But I have slides also with proofs, and if you want them, I can pass them to you. So the point here, there are two difficulties. The first is that we were talking about embedding into L2. Euclidean distances, okay? And the second instance is actually more serious because this is high dimensional, so it doesn't really serve the purpose. So the heuristic that I am using is this. I have a partial Euclidean distance matrix, okay? This is my graph, my initial graph. I complete it using the shortest path metric, okay, hoping that this is like a one-dimensional or lower dimensional manifold, etc. And then I realize it in Rn using the Fress embedding, but with a infinity norm. And then I project it to Rk with the L2 norm by doing PCA, okay? So PCA is essentially something that concerns the L2 norm. And then I obtain what I want. How good is it? It's not very good for normal standard measures, like, for example, are we preserving the length of the segments as the weights of the edges? So this test says that this is not a particularly good method. But my ultimate test was that I wanted to propose embeddings that would work well when I had to transform graphs into vectors in order to present them to a neural network. Okay, this is my quality measure. And this turns out to be the best among the methods that I've tested, which I don't really understand. I don't know why this L infinity norm works well. I'm still thinking about it. So another application. This is in dimension k for any k, correlation matrix completion. It turns out that insurance companies don't want to run risks. Bizarre. I never knew why. And instead of well, they have several strategies. First of all, they try not to pay you. Okay, they want your money, but they don't pay. Another strategy when this fails is that they try to estimate some of the risks, and then they try to complete the risk matrix, so these correlation matrices, where they don't have the data. Okay, so correlation matrices have certain properties, and they exploit these properties in order to complete them. But essentially, correlation matrices are a subclass of gram matrices. They're a subclass equivalently of PSD matrices. And so we are still back at a matrix completion, and we've seen also that this is equivalent to distance matrix completion. So it's all the same thing, so the same application. Oh, they look for a maximum determinant solution. I didn't read as far as to understand why. I don't know.
Low rank solution.
Yeah, well.
Maximum determinant would be the high rank.
This is this is maximum determinant, it's not even log max, but yeah, it's the same thing. But yes, I don't understand why. Actually, it's not that I don't understand. To be honest, I put this application in last night and I was too tired. The papers are there and they can be read, and maybe I'm sure there is a reason for this. Maybe they don't care about the rank. Debatable. I don't know. I should find out more stuff about this. But there's an interesting paper on the Royal Society proceedings or something by Hayam. Am I pronouncing it well? Hayam? Right. And there's a few sort of sketchy technical reports using various heuristics by guys in banking. And maybe the two of them together will give you a decent view of this application. All right. So, and now I come to the main part, in my opinion, of my talk, with some time to go. High dimensions are weird. The geometry there is not humanly understandable. It's depressing, and the things that happen in high dimensions scare me out of this business. I have been on the verge of leaving distance geometry forever for want of any sort of hope. Okay.
When you mention high, is from 4?
No, it's from 15.
Okay.
No, it's from 15. I'm not joking.
Why 15?
I'll tell you later. So, nearest neighbors. So the k-nearest neighbor problem is basically a cornerstone of a lot of different algorithms for machine learning, okay? And specifically, there is one that continuously calls repeatedly the one nearest neighbor variant of this problem. And this algorithm is very famous. It's called k-means, okay? So k-means is a heuristic. It's iterative. It takes a clustering that may be random and then improves it as much as it can, and then stops when it cannot improve it anymore. And it improves it on its combinatorial and alternately on its continuous side. So the combinatorial side is that these clusters may be reassigned based on the centroids that have been calculated, And once the clusters have changed, you have to recompute the centroids. And this alternates, okay? And every time you want to reassign a point to a cluster represented by a given centroid, you have to find the closest centroid, okay? So you have to find the closest point in a cloud of points, okay? So you have this cloud of points, which is very, very large. And you have a selected point. And the problem is, this sub-problem that is very important, to find the closest point. I mean, you know, you might think, okay, so I can just compute all the distances and choose the smallest. You know, if your cloud of points is not overly large, then you can do this. I don't even know whether there are other algorithms. For example, there are algorithms that cluster, the pre-cluster the points. There are algorithms for specific dimensions that are much more efficient. But let's stay with this silly algorithm, okay? It doesn't matter. Actually, the algorithm is of no importance here. Now, I'm asking you to see the problem where every symbol that was a variable or a parameter has now been replaced by a random variable, okay? So this is no longer a problem about points. It's a problem about distributions from which you are free to sample points, okay? So L is the set, the size of the set of points, and you have this distance function family that is parameterized by m, and it maps Rn times Rn, so this is the distance, so it has two arguments, u and v, 2 points, into R plus, the value of the distance. This parameter m, n is obviously the dimension, but this parameter m doesn't need, in the proof, it is treated completely syntactically. It is not linked to any mathematical entity, okay? So we are free to see it as we see fit. You can have m, I don't know, indexing a family of different distances, or you can have more simply, and what I advise you to do is I advise you to think about m to be equal to n, okay? We are sort of restricting the result. It's no longer as general as it was before with m, but it helps to think of m as n. And because m is completely free to be anything you want, it's not forbidden to think of it as n, okay? So this dn, let's say, is actually mapping, it's the distance in a certain dimension, okay? So the distance when it acts on points in R2 would be d2. When it acts on points in R3 would be d3. The distance itself doesn't need to be Euclidean. All right, so for each of these m, there is a random variable zm with some distribution over Rn. So this is the selected point, okay? So this random variable is, in fact, is a vector of random variables. For each component, there is one. And then for each point, there is a random variable representing the point, okay? So all the points are identically distributed. Z doesn't need to be distributed with the same distribution. Now, the minimum distance, which is the minimum over all the points between the selected point and the point itself, that is also a random variable because it's a function of random variables. And the same for the maximum distance. All right. So the distance instability theorem, which was worked out by this guy Bayer at Wisconsin maybe 20 years ago, or close to 20 years ago, is as follows. As m tends to infinity, if this quantity, p is really another generalization that doesn't need to be there. Think of p simply to remove the 1 over p in the p norms, okay? It doesn't matter. If this quantity doesn't get too crazy, and I'll be more precise later, doesn't get too crazy as m increases, then the closest and the furthest point are at about the same distance. So this is something that really makes me want to quit distance geometry forever.
Is this the 2 norm?
Can be 2 norm, it can be a convex norm, it can be whatever norm you want. In fact, it's a function of 2 arguments that maps into scalars. So really, I'm not presenting the proof, but the proof, it's incredible because it's a probability proof that I was able to understand. Usually I don't understand probability proofs. And this is one of those proofs that is completely syntactical. There's a few things that have semantics in the realm of analysis, and these are lemmata that are well known, like Slutsky's theorem, and the convergence in probability. And then the rest of it follows just by moving symbols. So there's nothing strange or bizarre in this theorem. It's in fact, I think it's a very easy theorem to understand. Okay. Now, what I really mean by this is the following. If the limit for m that goes to infinity of this variance goes to 0, okay, then the limit of the probability of the event that d max is actually smaller than 1 plus epsilon d mean, which is something that we don't want. We would like d mean and d max to be very far apart, okay? It goes to 1. So this is not exactly concentration of measure because it's really a limit that goes to infinity, and there's no evaluation of how the probability decreases. But I have empirical evaluations of how this probability decreases, and they're pretty sad. So this variance, what is it? This is the distance, okay, between the selected point and the ith point, and this is the average of the same value over the distributions, okay? So if you think about the Euclidean distance, I don't know, it goes from 1 in 1 dimension to square root of 2 in 2 dimensions, square root of 3 in 3 dimensions. This is the diagonal of the hypercube. And then square root of n. It kind of, it's not too crazy. Okay? The Euclidean distance is certainly a candidate. Okay, so what happens with k-means? This is how I came to know this result. It's because I tested k-means, I coded it myself, and my starting point was not fixed, but it was random. And every time I converged onto something completely different. I don't know if you can see the colors, but the reds and the greens have nothing to do with each other. We are in 100 dimensions, and there are 21 points. I mean, that k-means would be so crappy, there was something wrong. I thought I had a bug or something. And then I presented this thing, and then somebody in the audience said, oh, maybe it's the distance instability theorem. And I said, what is it? And then she gave me a citation, and then I dug it up, and I was very, very, very sad for a long while. So this is the loss of resolution, okay? This is epsilon. It goes from 0 to 1. So when it's 1, it means that the maximum distance is within a 2-factor of the minimum distance, okay? So it's only double the minimum distance. When it's 0.1, it's like d max is less than or equal to 1.1 d mean, okay? We're not talking about the closest and the second closest here. We're talking about the closest and the furthest. All right, so with a uniform distribution over 10,000 points, you can see that this has concentration of measure, even if not analytically, but certainly empirically, in that as soon as you have like 15, and this is 15. In fact, 15 is an empirical evaluation of the authors of this paper on k-means. If you're over 15 dimensions, k-means is very unstable, unless you stabilize it with different methods, which people do, okay? So k-means actually does work, but if you just implement it as it's described, it's a tragedy after 15 dimensions.
Which paper?
Sorry?
Which paper you mentioned?
Bayer, this thing, 1999, so 20 years ago. There's 4 authors. This is the first author. And maybe distance resolution or distance instability should find it.
Yeah.
Yes?
We had exactly the same experiment. While trying to make better heuristic for k-means clustering. We observed that up to 20 k-means is okay, but after that it totally fails to find a global minimum.
Yeah.
But just making a bit more sophisticated heuristic, and you can keep a stable
Yes.
behavior at least as you dimension 100.
Yes. Yes, that's true. This is why when you use k-means in the Python libraries, it works, okay? But this is much deeper than k-means. I'm not looking for a solution to how to stabilize k-means. I'm saying that whatever algorithm you are using, if you're over, say, 1,000 dimensions, you have no hope to distinguish between the closest and the furthest point. Well, you have some hope maybe to distinguish between the closest and the furthest, but imagine the closest and the second closest. Because this is what k-means really does. It asks you to distinguish between the closest and the second closest. If there is like 0.001 at 10,000 points of epsilon, okay, so maybe floating point can still detect 0.001. But God knows, if you have, I don't know, 10,000 points, what certainty do you have that you might really distinguish with floating point methods the closest from the second closest? And if you choose the second closest, it will not be good. You're making a mistake. And this explains this picture. Okay, every time a mistake is being made. Okay. Anyway, so uniform, normal, exponential, it's all the same story. now come to the second weirdness in high dimensions. This seems to be positive. So the earliest one was negative, and this seems to be positive. So suppose you have a data matrix, and every column contains a movie, okay? So this data matrix may have millions of movies, but certainly every movie takes, I don't know, a gigabyte, okay? So there's a hell of a lot of columns, and these columns are very, very high dimensions, and you have to cluster them. Completely hopeless, right? But YouTube does it. How do they do it? So one thing that people do in these cases is to precondition this matrix by a random matrix, similar to what I presented for Barvinock's algorithm. So this is a random matrix that is component-wise sampled from a normal distribution with standard 0 and standard deviation 1 over square root of k, where k is the dimensionality. And you get in return from this multiplication, you get this matrix TA. So it's got the same number of columns as A, all right? But the movies have become much shorter, okay? Much more compressed in a sense. This is a lossy compression, okay? But it guarantees an invariance. It guarantees the same invariance or a similar invariance to the one presented in the restricted isometry property. So essentially, the Euclidean distances between columns in the original matrix are approximately, all of them are approximately like the Euclidean distance between the columns of the projected matrix, WAP. And this barking of a dog, WAP, means with arbitrarily high probability, which means that there is a sequence of events that depends on k, and the probability of these events goes to 1 as fast as possible exponentially, okay? So the Johnson-Lindström lemma is the main result in this area, and it says that given this data matrix that has n columns and given an epsilon, there is a k, okay? And this k is really how short your vectors are becoming, is order of 1 over epsilon squared logarithm of n. Now, 1 over epsilon squared is bad, I agree, okay? But logarithm of n, and where is m? There is no n. So the original dimensionality is not here. So I find that this is magic. I found for a long time that this was magic. I used it in, I applied it to mathematical programming. I obtained results that kind of worked. Incredible. Anyway, so this Johnson-Lindström lemma, the T is sampled as I told you before, and the probability that A and T are approximately congruent exceeds 1 over n. This is not an easy proof getting to here, but once you're here, you invoke the probabilistic method, and then you conclude that this T exists. Now, in practice, theoretically, you should need to resample T many times. I don't do it. I don't do it because it's expensive to resample it many times and check whether it actually preserves approximately all of the Euclidean distances. So instead, what I say is, the probability, if you sample it just once, most of these things will hold, but not all of them. So there may be some pairs that don't hold, but there's not very many of them. There's not very many because, in fact, this is what concentrational measure really means. Okay, the discrepancy from the mean is very, very low. It's very unlikely. So you might be incredible. In order to get them all wrong, it would be more unlikely that a comet would, plunge on the Earth right now. So, in fact, I'm pretty sure of myself when I say just sample it once. It's okay. The other thing is that k is independent of the original number of dimensions, and this is also magic. So it seems like your choice about the number of dimensions made no sense at all mathematically. It was very arbitrary. In fact, it's the number of things that you're embedding in the space that makes a difference. Go figure. I don't know. Anyway, so are there relations between these two results that are weirdness in high dimensions? I don't really know, but this maybe I don't have time to go into, but this. I said that the random projections are magic, and they may well be. However, in random projections, we are losing an epsilon. On the other hand, the distance resolution theorem tells us that all of the useful information is within an epsilon. Am I losing the good epsilon? So this would re-equilibrate, the no free lunch theorem in a sense, right? I can't have magic for free because there's another result that tells me that I'm losing whatever precious I thought I had, I'm losing it. I don't know whether I'm reasoning by analogy here. It's not an inference. So I have no proof, not even a statement of anything. I'm just reasoning about this analogical symbol epsilon that appears in both results. And if it's related, if the two epsilons are related, then we are in deep trouble. Okay, so very last, this is really the conclusion where I wanted to get. I have an artificial neural network, which is basically a dynamical process on a directed acyclic graph. And the nodes that don't have incoming arcs, they are the input nodes. And the nodes that don't have outgoing arcs, they are the output nodes, okay? And then there are weights at the vertices and weights on the edges. There are two sets of weights on the vertices and one set of weights on the edges. And there is this training process where I present a training set on the inputs and I obtain an output by evaluation. And then I have to choose these weights in order to minimize the error between the output that I obtain and the output that should have been obtained, okay? And I process this network until I exhaust my training process and then my training set, and then I can start proposing new inputs to the network and hoping that the network answers me with a meaningful output, okay? And then I have this problem. I have a set of sentences in English, and I can represent them as graphs, or I can represent them as incident structures in a dictionary. But neither way, I can present them to a neural network. What people do in this, people use neural networks for natural language processing, okay? So how do they do it? They do it in two ways. Either they have, no, they do it in one way. They have an incidence vector for each word, or for each sentence, sorry. And then they either have this very large neural network with a lot of inputs that takes the incidence vectors, or else they project their incidence vectors randomly so that they are somewhat shorter, okay? What I did instead is I transformed each sentence into a graph by using incidences of words into a dictionary, but this is now a graph, okay? And I'm free to also introduce semantic similarities in the graph, which I haven't done for this test. But now I have a graph, and I can run all of the methods that I talked to you about during this talk in order to transform these graphs into vectors. Of course, I obtain vectors of different sizes, so I have to pad and then I have to reproject. I mean, I have to do a certain amount of house cleaning before I have a training set with all vectors of the same size, and each vector represents a graph, okay? But I got there. And then I ran these tests, and what I obtained is that in the traditional setting, I have higher loss and smaller accuracy than with this approach, okay? And this is very meaningful because essentially what I'm using here is a very small network that I don't even know whether this network is good for the kind of task that I set it to, but everything is equal apart from the presentation of the vectors. So these vectors are different. And what I found is that for SDP and for DDP and for PCA and for isomap, I didn't do better than what is being traditionally done, i.e. A set of incidence vectors projected, okay? However, when I started using the Fress embedding and my heuristic for mapping it first into Rn and then Rk, then I got much better. Well, maybe it's not much to you, but I think that these kind of numbers excite people in neural networks. So I'm here. I don't know why this works, but this is the beginning. But it took me 2 years to get here, so I'm pretty happy. When I talked about these topics at CNMAC, I didn't have this test, and it took me 2 years. Maybe because I'm too busy to actually devote time to this, but now I got there, and I'm very intrigued. I don't know why I opened so many questions. In the meantime, there is this threat from the distance resolution theorem. I don't know what I'm doing. Maybe everything is random because I can't distinguish distances. Anyway, thank you very much for your attention.
I have to say that much better than the talk that you mentioned.
I know, it was the first time. I apologize for that.
Question, please.
Yes.
Was that T matrix, is that the one that's called sketch matrix by some people?
Yeah, so some people call it sketch matrix. It's actually, so it may be the same matrix, but there's a different analysis. So people do sketching, they work on subspace embeddings, which means that the matrix is a good projector for a whole subspace of points, not just for a discrete set of points or a finite set of points, okay? So it's a much more powerful result in a sense, but it also comes with a different approximation guarantee. I think it's additive rather than multiplicative. Yes?
Could you give me an intuition for that distance problem?
So which one?
The 1 plus epsilon.
The Johnson-Lindershof lemma?
The longest versus the shortest.
The longest versus the shortest.
Why the largest?
Why the pairwise distances are being kept almost invariant?
Yeah.
Can I give you, I don't know if I can give you an intuition. I mean, as I said, it's very difficult to get an intuition of high dimensional geometry. But I can tell you this. The concentration of measure phenomenon acts in many cases, and it acts, for example, on the surface of the sphere. Okay? So if you have a surface of the sphere in 3 dimensions, and I'm asking you, for example, to give me a height on the pole so that the surface around the equator takes 50% of the surface of the sphere, or 90, let's say 90%, you'll be pretty close to the pole. Okay? Yep. And then in 10 dimensions, you will be at half the height between the center of the sphere and the pole. And in 100 dimensions, you'll be very, very close to the equator. And then in 1,000 dimensions, it will be indistinguishable from a line of the equator. But here's the thing that will crush your mind for any equator. So suddenly your intuition that sees this thing getting flat is not true anymore because it's every equator.
Any more questions before the break? So let's think again.
Thank you.